Hi everyone, my name is Henny Edmoni. I'm a faculty in robotics here at CMU, and I am just here as the opening act to introduce today's speaker, Nancy Pollard. So I'm really excited to introduce Nancy. Nancy was actually my faculty mentor, so this is like, I get to pay back a little bit of the advice that she's given me. Nancy's a professor in both robotics and computer science department here at Carnegie Mellon. She got her PhD in EECS from MIT, which you may have heard of. She has decades of experience doing dexterous manipulation and trying to get human level dexterity into robots, which is a huge and challenging and ambitious goal. And I'm excited to learn more about what she has to say about that today. Nancy has many awards to her name. She has a career award and an Okawa Research Grant. And most recently is part of this NSF Convergence Accelerator, which is intended to take what we do from the lab and turn it into practice in reality. And as part of that, she has a new company called FuturHand Robotics. That was spelled singular hand, where she is the co-founder and president. And they are working on dexterous hands, testing already in factories from Bosch, and clearly making an impact in the world of robotic dexterity. So let's welcome our speaker, Nancy.
All right, thank you for that very nice introduction, honey. All right, welcome everybody. I'm going to give a little bit of an overview talk. I want to start out with a little bit of just visuals on what I mean when I think of dexterity. So to me, dexterity is things like picking up that wrench in order to use it. And this is old footage of some slow motion video we collected a long time ago to really just look at all the things that are happening, how the fingers kind of maneuver their way underneath the wrench, how we do those little fine motions in order to make sure we're holding it in our hand in a way that we can manage it and apply large torques. And this is another example where, there's not really any room there, and this is a hot plate. So the person has to kind of, my student called it bicycling the fingers up, bicycling the box up in order to get it off the plate. And these are just in-hand manipulation. Maybe more common to what you might think of when you think about dexterity or in-hand manipulation types of activities. But these little adjustments, we all know how to make them. We make them all the time without thinking about them. Every time you pick up a pen in order to write with it, or take a tool and pack it into some some other part of your hand so you can use your fingers to do something else. I want to put this up here. This is my favorite definition of dexterity. I've used this for many, many years. This comes from a book that was written in Russian in 1949. It was published, and it came out in English not so long ago, back in 1991. There's another version in 1996. And you can find dexterity, the ability to solve a motor solution for any external situation, to adequately solve any emerging motor problem correctly, quickly, rationally, and resourcefully. And what this guy, Nikolai Bernstein, did is he would study athletes, he would also study workers. And what he found was that people, even very expert folks, would not do the same thing twice, right? If they would always hit the nail with the hammer or whatever they were trying to hit, but the actual motion would always be a little bit different. And so he was trying to understand what makes us able to do that, able to always hit the target with these varied motions. How do we use that adaptability in order to solve the problem in the way that we need to solve it? And so there's a lot of, if you are looking at the world through an AI lens, you can see a lot of artificial intelligence types of things here. Like we need to use intelligence in order to solve a dexterity problem, even if it's a motor problem. Like, it seems very simple, hitting a nail with a hammer. This is just a little bit of a preview of some of the things we've worked on from the DARPA Manipulation Challenge about 10 years ago or so, to trying to designing some of our own robot hands. I get to that, working with the Robonaut 2 hand, working with bell pepper harvesting, working with the shadow robot hands. And this is Herb, if any of you are old enough to remember. when Sid was faculty here, Sid Srinivas, doing some at-home tasks like plant watering. So there we were thinking about, well, how do we, reconfigure an item before we pick it up, the way that people often do in order to pick it up more in a more convenient way for ourselves. So I want to focus a little bit today on things I call sort of the last mile problem. So we've seen some successes recently with, say, food handling. Soft robots can do pretty well at picking things up and putting them different places. But the things that we can't do with robots right now that are really, really hard are things like this. So this is a torque sensor in one of the Bosch factories. This is a power steering column, and we have permission to show this. This is a little connector that's dangling down, and this moves a little bit, so the person's kind of securing it here, and they're pushing it in with their other hand. And this is something that they'll do repetitively. They will do hundreds of these during their shift, and then they'll take a break, and someone else will come in and do this for a while. So that's one example. Here's another one in agriculture. Bell peppers seem like they shouldn't be too hard to harvest, but they have been a bit resistant to automation in the field. People can do them in greenhouses where they sort of string them out so the bell peppers are just sticking out there. But they haven't been able to really do them in the field, partly because the peppers grow every which way, and partly because it's sort of a two-handed task in a way. You have to grab the pepper with one hand, at least this is how people do it, grab it with one hand, cut it with the other, because you can't twist them off or you'll damage too much of the plant. Peppers get harvested over weeks. And then there are other challenges like better prosthetics. How do we do medical care in remote areas? How do we do home care with robots? These kinds of challenges we're really just beginning to touch. So these are some of the things we're interested in. So in today's talk, I want to talk about what do we need to do? How do we need to move the needle on some of the things that we're working on in order to really address these last mile problems and get robots out there doing these things. So I'm just going to throw a bunch of ideas out there and show some recent work that folks in my lab have been doing. First one is that dexterity requires compliant interaction. So this is just something I have believed for a long time to be true. And I'm going to show this video here as a little bit of just kind of evidence about this. So when we watch this person these are just pick and place tasks, but they're constantly, where's the pinky is getting caught in there? I don't know if you saw it. They're always hitting things. So banging into things in this slow motion video, either with the object, with their hand, it's just part of the process. And I did not really cherry pick these. It's pretty much every interaction. And the next one, you'll watch the gum hitting the side, being slid over. You can imagine that they're collecting information, like she's collecting information as she does this. Or you could imagine that these things they just naturally happen. And as they happen, we make adjustments. And if you're into the kind of neuroscience angle of things, we did count the time lag between the kind of errors and I'm going to go back to the compliant part while I'm still talking. We did count the time lag between what might look like an error and what might look like the reaction, and it was usually about 100 milliseconds. So time enough for us to process that interaction, for the brain to send a signal to the muscles to respond. So these kinds of collisions happen all the time. It's really good that our system's compliant and we're not, breaking everything or ourselves as we run into these objects, and we're able to make these adjustments in terms of errors as we go. And you might have noticed with the tea bag, she eventually gave up. So we don't always succeed. So that's compliance. This is another example. So this is our collaborator, Brett, who's a nurse anesthetist in Pittsburgh. So if you have been put under for something, he might have done it for you. He might have given you your anesthetic. So he takes 3 different prosthetics with him to work because he doesn't have any one prosthetic that can help him completely do his job. So he's rigged up his station. He can put his different arms, his hands up on the station, and then he just kind of swaps between them as he does his work. And sometimes he doesn't use anyone at all. He just uses the residual limb that he has. And part of it, here he's showing one of his frustrations, the slate. He's like, I can't even pick things up off the table. And you can see here, part of the problem is that this prosthetic, which he favors over the really very fancy one that he has at home, which costs, I don't know, $100 and some thousand. Once he finally forced it through insurance, he keeps that one mostly at home because this one works so much better, but still it's not good for this task. And part of the reason it's so rigid, it can't really, it's so rigid that it can't kind of just give him a nice soft contact surface. And the contact forces don't line up well for these objects as he closes the grip. It's not made for these kinds of interactions. So compliance can help a lot. This is showing one example of a compliant robot hand that Dominic here designed and put together. And it's able to pick up small objects. It's resistant to damage. It's not going to have a problem with this kind of... So this was the only one he had at the time. And it would have taken him a while to make another one. He didn't mind, kind of slamming it into the table. So that's a good sign. And these kinds of hands we've taken out into the field as well. So this is the bell pepper harvesting system that was deployed out in Iowa. And you can see 2 arms there. One's a gripper, one's a cutter. It's being teleoperated by a person in this example to collect some data. You can think of collecting data for training an automated system later. And this will give you a little bit of an idea of what's going on with this system. So this is being teleoperated, so it could potentially move much faster than this. But this is already faster than our autonomous systems that had been deployed in previous years where we tried to do this one-handed. So the soft gripper enables grasping the peppers and pulling them out in a way that doesn't damage the crop and can adjust to the individual fruits. Okay, so a little bit of comments about compliance. I'm going to move on to the next thing. So a lot of times we think about trying to transfer interactions from people to robots. And I'm a big fan of this, in part because I think there's so many interesting things we can observe from how people interact with objects, and in particular in the very fine detail of how they do it. So I was pointing out some of that with the wrench pickup. So my comment here is that if we're going to do this kind of transfer from human to robot skills, if we really think about the contacts that are involved, this kind of transfer can be very effective. So this is some little bit older work that first looked at this kind of from a whole body perspective. So thinking about, all right, where is this individual contacting the box, and what functions do these contacts have? And can we program in safety margins so that whatever the new geometry is, we can ensure that we can accomplish the task with, maybe not more than double the amount of contact force that we had in the original. So can we make these kinds of guarantees? So it's kind of neat if we can do that and provide a little bit of flexibility for where the hands can be placed. This is a little bit of a follow-on of that work that just appeared this year. So the idea behind this one is that was all very fine, but these areas, which are called independent contact regions, they give you a little bit of flexibility for where you can flick your fingers. And one of the reasons that they're nice is because in this world of so much uncertainties, okay, I'm looking at this thing with vision. I don't exactly know a lot of things. I don't exactly know maybe its size. I don't exactly know its mass distribution. I don't exactly know its friction properties. I have a lot of uncertainties. Anything I can do to help me adapt to uncertainties, here we're looking at uncertainties in our solids estimate, is really helpful. So uncertainties in position. So this is a fully soft hand. It's a foam hand. I'll talk a little bit more about it later. It's one of our educational hands that we put together. This is Jonathan King's work, along with Harmur Alawalia, who's a high school student, but who's working with us. who will be applying here next year. So maybe we'll see him around. The idea behind this work was to say, all right, well, this technique has been around for a long time, but when we get beyond 2 or 3 contacts, it's really, really slow. So this work proposed a very fast algorithm for, I should just start playing the video, for
link contact regions can be
I
used.
don't want the audio. A very fast algorithm for doing this. That's sort of a divide and conquer algorithm that could get up to about 7 contacts, and it's also an anytime algorithm. So it's returning, it can return in real time. All right, where should you be putting your fingers? And this is unnecessarily slow because we had just put this gantry, this educational gantry together. Like I said, I'll talk a little bit more about this. I'm trying to figure out where the clock is in this remote so I can keep track of the time. It's broken. I'm going to get my sewing. Excuse me, y'all.
So what, might give him 10 minutes,
Otherwise, I'm just going to talk and talk for arbitrary amounts of time until one of y'all gets up and stops me. Okay.
You also have a watch.
Oh, I have a watch. Yeah, bravo.
This me an embarrassing story.
Yeah. All right. I always collecting embarrassing stories, so thank you. Yeah, so this is a little bit of how it works. I'm not going to spend a lot of time on this because I just looked at my, didn't look at my watch, but I looked at my phone. Okay, so 2 contacts on a surface can be thought of, where do you put the first one, where do you put the second one? We can order them. You only have to look at half the space. Now you have this triangle within which you're going to search for contact regions. Large contact regions end up looking like big squares up there. So with the orange region, the green region, it doesn't matter where we put them, as long as all those grasps are good, based on something we categorize as good, we're happy. And now you could brute force just find them all and find the largest box or largest of any kind of region. Why is this cool? This is cool not just because we have uncertainty for where we can put the fingers, but we can do things like rolling and sliding, and we know that we're not going to lose the grasp. So if I'm thinking, all right, I'm going to hold this thing, and I'm going to now slide the thumb along, this is something we do all the time. Like every time we adjust our pen or a screwdriver or a hammer in the grasp, we're sliding our contacts around. So we want to be able to think about what regions enable us to do that. Okay, so now we're going to Delaunay triangulate this space. This can be 7-dimensional. It's just 2-dimensional for illustration. They can still do Delaunay triangulation. These purple things are where we know there are bad grasps. Inside any of these circular regions, but by the Delaunay property, is an empty space. Those empty space could be good grasps. Let's look in the biggest one. Maybe we'll find the biggest region. That's the idea. And then there's a little bit of stuff here about what you do on the boundaries that went on and talked about today. And so then we look in the biggest region and we keep doing that until we find, we're going to grow a big region in the in the largest possible space until we find a bad point, and then we just keep those good points around until we can guarantee that we found the biggest one. And at any point, it's an anytime algorithm. We can say, all right, this is the biggest one I have right now, and just kind of return that. And someone could use that to do their grasping or grasping.
Do you ask questions? So do you search this 7-dimensional space?
We Delaunay triangulate it.
I end up triangulating in front of one eye.
Yeah.
Which was the biggest circle. So the other question is, I was curious, what makes things connected and disconnected in that space with the light gray, blue triangles? Is there
why are they color coded that way? They're color coded based on size.
I mean, why are they disconnected? What does disconnectivity mean? And you have a connected set of.
They shouldn't be disconnected. Oh, over here.
Yeah.
These are just the ones we've. These are the light blue ones are ones that are good grasps. And you're asking why good grasps will be disconnected from bad ones.
Well, what's the connectivity? What happens in the connectivity change? I'm not asking.
You fall out of the friction cone or something. Second, right? Yeah. So so that's we can talk more offline, but And that's the basic idea of that. So that's what I wanted to show there. So this is one way of doing a little bit of grasp analysis that's helpful for analyzing manipulation tasks such as rolling and sliding. Although we're not doing it here, we're just using it to pick nice grasps that are robust to size errors. Okay, so another thing I wanted to talk about is contacts are not points, they are areas. And we often think, even in that previous work, we were just thinking of them as contact points, which is not very good. Because when we look at real world pictures, we see areas all over the place, no matter what we're grabbing, especially if we're grabbing tools like a hammer, a screwdriver handle, even this plate, we're going to see big patches of areas. This is old work by Kamakura that where they use traditional technique of just inking the object, grasping it, opening the hand. Where do you see the ink? That tells you the contact areas. But these days we get that information through motion capture. It could be thermal imaging like in the contact DB data set, or it could be motion capture looking at proximities. So proximity between this mesh. Now that we can get really nice meshes of human subjects and the object meshes. Now that we can get really nice meshes of objects. So we get contact information that looks kind of like this. And I think it's so cool that we can look at this now. It's been, you have wanted this information, this kind of data for a really long time. Now we have it. The classical view is this, where we have these point contacts. And if you look in textbooks, these are the kinds of things you see. All right, we have this point contact. We can think about contact force, contact position. And maybe this is okay for these old. And this is also maybe a little embarrassing because this is what I did for my PhD was pick up toy airplanes. But that was pretty rigid. And those contacts are maybe point contacts. But with anything that we're working with today, most robots have some sort of padding on them. We're working with fully soft robots. Even if you're thinking about inverse kinematics from an animator perspective, if we're just saying, all right, match these points from the hand to the baseball, we get something that looks pretty like not good. But if we say match these big fat areas, we get something that looks much nicer, I think, because you're expressing more of what you want. So what we have done, and this is work of Arjun Lakshmapati, is to represent these contact areas as patches, slight little bit of detail, not too much detail, is we're going to represent these as an axis. So an axis is really just a starting point, a direction and a distance, turning angle, distance, turning angle, distance. So you sort of walk your way along a surface. And I just really am a big fan of all the geometry tools that are coming out in computer graphics these days because they make this kind of thing really, really easy. And we worked on this project with Nicole Fang, who's one of Keenan Crane's excellent students. And thanks to Nicole for helping us hash all of this out. So we have this axis, and then we have this representation of contact points relative to the axis, where every point is expressed by its distance away from the axis and an angle. So you look at the angle, a distance away, you can walk out to the point. And what that gives you is a way when you have some other surface, you can retrace this contact path, just like putting a decal on. So you peel off the decal from one surface, you put it on another surface by taking the starting point and direction and just walking your way out the axis and then attaching every contact point that you have. So that's what we do for contact patches. And this is I'm not going to go through that detail, but this is a really convenient model for letting artists work with this representation. So we created a tool that allows us to kind of paint on surfaces. So you could paint on the surface of a hand, say, all right, I want to take that light blue and I want to put it over there on the mug. And same thing for these fingers. And let me see what grasp I get. And I don't like that. I want to move the middle finger a little bit. So you move the contact patch just as a whole thing. And then, the artist can work with these contact areas. They don't have to work with all the little fiddly joints in the hand or do inverse kinematics and try to make the contacts match. And this is a really powerful way to edit and modify things. So I'll give you a little bit of a look at what this looks like. This is showing some of the operations. So you can rotate the contact patches, you can translate them around, you can bend them. You might wonder why you want to bend them, but if you think about grasping a softball or baseball, and you want the side of your finger to go along the ball, but you know your finger's going to be bent, you can still paint that whole patch, and then on the ball you can bend it, and that will cause your finger to curve, right? So you do need things like that. And then you have a matching process, very dense correspondences, lots and lots of points on the hand, matching lots of points on the ball, and then you just minimize the distances. So that gives you a really easy downhill optimization to solve. And you can get, it doesn't really matter what, Arjun would argue with me, but it doesn't really matter what optimization you use. You can get some pretty nice looking results at the end. So I'll just show some of them. These were all created by specifying where the contact should go. And I'll play this one. Of course, it can change over time. Contacts can change over time. And here's another example of just interpolating the contacts. If you really play baseball, you're going to complain about this one, but for an amateur looking at it, it was a pretty good start, I think. And then this is just to show it's not all about hands only. Contacts anywhere by anything could be handled this way. And in fact, Arjun has a follow-up paper in CVPR where they take images and represent the contacts and come up with 3D representations of what the people are doing in those images. So that you can look up. I didn't include it here. So these are some things that amateurs created using our system. We gave them the objects, we asked them to hold them, and then create a representation in Maya. They had 1 hour to do five results. And I think that the results ended up looking pretty good. Of course, we want things to move. So this is showing an example of some follow-on work where we're taking those contacts over time that are captured and then mapping them from one hand, like motion capture hand is, I think, the top left one, and then mapping them to all these other hands, both robot hands and that top middle one is a robot hand we made. This is a Lego hand, and then some computer graphics hands, and then having them all do the task by matching the contact locations. The way this works is that the artist will specify where these correspondences between certain features. And you can remember those axes, the way we represent contact areas. We do the same thing here. So we draw, in this case, 5 axes representing the 5 fingers, 4 fingers and a thumb. And those sort of divide up the area of the hand in such a way that every contact on the original hand gets associated with one of those areas, and it can be redrawn on any new hand. You have to make some decisions, like is Baby Yoda going to take its 2 fingers? Are they going to be the index and middle, or are we're going to combine the index and middle and the ring and pinky? So the artist makes those decisions, and once those decisions are made, it's all automatic. So this is just showing the contacts and how they map. Hopefully that looks intuitive. It's all, like I said, once the artist specifies the correspondences, it's all automatic. And then this is showing the motions that result. These are all from the motions from the grab data set. And then we included some size variation just to show that it can accommodate pretty sizable variation in size and still perform the task. And then these are some two-handed interactions from the Arctic data set. There's nothing special about them. A limitation is this is all kinematic. It doesn't look like it. It looks like it could be simulated. It's not. It just looks so good because the contacts are considered. But this result will show you that it's all kinematic. If the apple's too big and it can't stretch the hand far enough, it walker will, fail. So, yeah, that's that. Right now, we're working to add forces. So this is a robot bathing project, and we're capturing skilled caregivers giving chair baths to individuals with pressure gloves. So we'll have the contact information as well as the force information both on the hand and on the surface of the body. And so that's what these videos are showing. So the ability to, let me clear this again, the ability to track both the body shape and the hand shape. This is early results. The hands have gotten a little bit better. And then those contact locations on both the hand and the body over time. And so we can see where are people applying forces, how much force does it take, how does the hand conform to the object. And those things will help us design a really nice hand for robot assisted bathing. Okay, I want to say a couple more things, but I'm going to speed it up a little bit so we don't run too far over time. Next thing is we can design for dexterity. So one of the things I've become really interested in over the past 8 years is designing our own hands, because I got so frustrated with the robot hands that were out there. And I really believe we can design better hands if we have highly detailed task information. I'm going to show one avenue of this. This is Sunyu Wang's work. He was looking at these clay sculpting tasks and had this idea that a lot of things that are happening are based on they can be characterized by these foundational poses. So here are 3 different poses by the same hand in the same tool that function in different ways. So you can watch the movements. It's kind of like the hand is forming 3 different simple machines, simple mechanisms. So what if we could design a robot hand? It doesn't have to be as complicated as our own. It can form these 3 same mechanisms, and he did design and build one. And the hypothesis that he made to make this easier is if the tool in hand could get into that pose, the single pose that I showed in the beginning, this pose here, then they would be able to wield the tool. He made that hypothesis. He tested it. He said that if this was true, he found that like 99.9 roughly % of all hands could wield the tool a little bit. Some were better than others, but this hypothesis was a pretty good way to sort out hands from the beginning. So he set up a design process where he built a hand template with parameters, and he would sample that entire space. This is just a 2D representation, but it was a 9-dimensional space. He would just kind of try to fill it up as much as possible with samples. And test, can this hand that I'm sampling get to the foundational pose? He used an RT algorithm to do that. So just check your closest pose, adjust it a little bit, see if you can get into the foundational pose. If you can, keep it and add it to your tree and just keep kind of building that out. So that's what he did. And then based on those results, he chose one hand and constructed it. And this is showing an open loop, not even with any control, really, from the kinematic results performing those 3 maneuvers. So it's not, so beautiful. Yeah, you'd expect to have to add some closed loop control to make it really function well. I want to add a quick aside here, which is that we can actually analyze fine manipulation directly on meshes. So this again is like a call out to the usefulness of today's geometry processing from computer graphics in the robotics domain. So this is again Samyu's work with Arjun Lakshmikwati. And the idea is that we have all these great models of real world things that we use in our world, like utensils, tools, and they're usually represented by these mesh models. And they're not always really primitives. Like was made probably with some CSG process, but it's not one simple primitive. It's not just a cylinder. And the same thing for the hands. The hands are maybe composed of a bunch of simple primitives or CSG operations, but they're not, except for these fingertips, which are cylinders and capsules, they're not entirely simple things. So what if we just say, all right, I know I have a mesh. Let me just not make this assumption I have a primitive here, like a cylinder or a locally smooth shape, but let me just use what I've got. I'm going to follow the mesh in order to even to think about sliding, to think about rolling. I'm going to follow this mesh surface exactly. And so that's what they did in this paper. And I'm just going to show some results quickly to give you an idea of what that looks like. So they're able to analyze these kinds of interactive rolling and twisting motions and how they look like, how contact is maintained, and think about what kind of forces could be applied on the meshes, acknowledging that you have a mesh for the hand, you have a mesh for the tool, and even those meshes might be very complicated. So this one's a little bit wonky because the tool has a knurled surface, which is, it probably should be approximated, but wasn't for this paper. And even here, there's some rolling going on. It doesn't seem like very much, but in order to do this motion, your fingers kind of roll on the surface of the tool. And I think this will become more and more important to think about as we try to have more and more fine control of these sorts of manipulations moving forward. This last one. Okay. All right, I want to say a few words about education. I mentioned this educational toolkit a little while ago. So if we step back and think about the big picture, you know, we can think about we're heading toward a world where we're going to have more and more robots around us. And so we want to be thinking about, well, how do we get the word out there, get tools out there, have people able to grow up and, you know, kids able to grow up and use and think about dexterous robots. So this is a toolkit that we put together. It's really version 0. It's a self-contained platform. It has 16 degrees of freedom. There are, the gantry is 3 degrees of freedom. There's a roll. So the hand can roll like this. You work with a hand surgeon at University of Pittsburgh, UPMC, and he says, like, if you have that, you know, even if you fuse the wrist, people have a lot of capability. You know, you can fuse the wrist completely, and people's, like, maybe reaching up into shelves gets a little bit hard, or reaching, you know, down under things or around things, but this roll is like the most important thing. So we added that for the first version, and then the hand itself has 12 degrees of freedom. 12 is tendon driven, and the complete kit costs about $2,000. The way the tendons work is that this is a foam core hand, solid foam, and it has an inner glove that's glued to the hand, and tendons are sewn in. So you can sew them any which way. You can explore with any sort of anatomy that you like. So if you think the flexors and extensors are most important, you can start with those. If you think these little lumbricals and interosseous muscles are really, really important, you can throw those in. If you want to create your own muscle and think, you know, you can do better than the human hand, or if you want to design an entirely different looking hand altogether, one with 2 thumbs or something, you can totally do that because it's just built around a mold where you have a mold, you inject the expanding foam, you have to create a glove. So we use a human-like hand, so we could just buy a glove off the shelf. But you have to have the some kind of fabric coating you can sew into. But beyond that, you have like you can do anything you like. So it's very, very flexible. And we've given this to people, and they've started to carve into the hand and use buttons and you know, kind of all kinds of arts and crafts in order to see what they could do with it. So that's pretty neat. This is the gantry. It's quite straightforward. It's actually a modified CNC router, hobbyist router. I mean, it costs a little bit of money, but it's not so high end. But it will definitely take the weight of this arm, and it would probably could be modified to be a 2-handed system. And it's customizable, modular. We're going to give it a little bit more Z height in the next iteration. This is just a comparison to some of the different hands that are out there. This is not the least expensive hand itself, but it's pretty much down there. Degrees of freedom are, anything you like I said before. Actuation 12, it's in the middle range. It's pretty anthropomorphic, more so than any of the, I would say, because you can make it, you can dip your hand in alginate just like in Hollywood, and you can make your own hand very easily with this method. It's fully soft, open source, and the full kit is available too, so that's nice. I will make a call out to Kenny, who's putting together also a full kit. So you're going to be our competition. That's great. So we were able to demonstrate this. We have a travel version. We were excited to go and show this to some congressional staffers back this summer. So that was a lot of fun. And we also put on a research experience for teachers, one-day workshop. So those videos we're going to have posted at some point on the RI YouTube website. You can take a look. John will also be holding a workshop where people will build these. And if you're interested in participating in that or finding out more about that, you can let me know. Okay, so this is just a few quick demos of what this hand can do. Again, this is our travel version, so it's this is less capable than the one that's on the gantry because we take it around places. So I think it has 5 tendons, so this is just showing it doing a few tasks. One really cool thing is because it's fully soft, it can operate scissors and these hemostats. No problem. Because the softness of the mechanism allows it to comply and accomplish these tasks. And I'm just going to skip that one. Okay, so back to the last mile problem. Henny mentioned the company. The company is working on problems like this. So trying to do this sort of plug-in task. And they have a process. We have a process to look at the task, take the details, create a hand, put the hand on, transfer the skills. And the goal is to do this in as little as 5 days. In fact, this demo was created in 5 days. It's sped up though. I didn't put the X on there, but this is a sped up video. We're almost down to that speed now, without speeding it up. By the way, if you're looking for internships, the company will probably be hiring interns very soon. So you can reach out to me for that. Okay, so quick summary is that today's talk, I mentioned a few things. So one is we need to have compliant interaction. We do that with soft hands. We believe that those soft hands help us solve a lot of problems just by their inherent softness. And yet we're still able to do very kind of fine manipulations with them, both through teleoperation and autonomous learned processes. We've looked at a little bit of human robot skill transfer. I think if we're going to do this, we should really be thinking a lot more about contact, what contact we want to achieve, and how we make those contacts robust to uncertainties and errors. Contacts are areas we need to be really thinking about that and work that into the way we analyze tasks, and then we can design for dexterity, design our robot hands, augment our robot hands to do specific things if we know what the details are for what we want to do. And then I talked a little bit about analyzing fine manipulation on machines. I want to acknowledge my really amazing team of students. So Dominic has graduated. Cornelia, John, Arjun, and Sunyu are still here for a little bit. And they work on hand design, manipulation, analysis, applications, and education. And then I just want to acknowledge everyone else that has been working with us for a while, as well as our various funders. And thank you all for coming. And I'll take questions. Thanks. All right. Yep.
I'm curious on your thoughts on, I feel like China has been manufacturing some interesting dexterous hands, such as from Shockwave and Muji Robotics. I'm wondering if you've seen them and what do you think about them, and I guess like as more people are.
Yeah, absolutely. So,
Please repeat the question.
sure. So the question is about what do I think about some of the robot hand hardware that's coming out, and what do I think about what do I think we need for tactile sensing? So, every time I go to a conference, there are 15 new hands being demonstrated. That's how it feels, right? So a lot of people are really racing to build hands and new hand hardware, and there is a lot of variety out there. It's a very exciting time from that perspective. I feel both excited and I feel extremely disappointed when I look at them because the excitement part is because people are really looking at this now and trying to solve this problem. There's a lot of attention on this problem right now, so that's great. What disappoints me is that many of these hands are on exactly the same one. So you could take, the Robonaut 2 hand, or you could take the Utah MIT hand for that matter, going back even farther, and say, well, what are the differences really? Are there any substantial differences in the basic layout of, how are the fingers set up and where are the motors and what are the degrees of freedom in the workspace and the ability to apply forces and coordinate the interactions of the fingers. And I'm not seeing that because I don't think people are thinking about that so much. I'm not thinking about what does this hand need to do. They're kind of looking at the human anatomy and simplifying it. And I really feel that's not the way to go. So I feel a sense like this disappointment that comes from my frustration for trying to use all of these fancy, expensive robot hands and finding that they, for instance, the shadow robot hand was amazing. And we had one of the very first shadow robot hands here, still in my office. When they fully close the fingers, there's an enormous gap in you, right? So you can't make a fist. You can't close around small objects. Even to pick up that frying pan I showed, we had to put big wads of foam in there, right? So it's like, okay, did they not think about that? So this is what I get frustrated about. So that's the hands question. Tactile sensing. So Cornelia is one of my students. I didn't talk about her work a lot. She has a paper that's going out very soon looking at tactile sensing for soft robot hands. What do we do about it? So that's coming soon. I don't want to steal her thunder. I'll let her talk about that. And you can reach out to her personally if you want to find out more. What I always say about tactile sensing is what we need is tactile sensing everywhere. I don't care if it's very detailed, but I want to know if I contacted somewhere. I want to know. You have to tell me. If I contacted on this side of the thumb, just at least tell me I contacted on the thumb. Tell me something. Right? So don't just say, I can't tell you anything unless it's on the fingertips. That's very bad. So I want some information everywhere. And then I can work with that. That's my first thing about contact sensing. I won't submit.
So you would think an accurate Boolean contact, no contact read would be more valuable than a detailed course.
Yeah, I do. And obviously when people have these detailed force informations in localized areas, they're able to do amazing things with them. If the things that they can do with them are limited to the, when they can keep the contact on these areas, right? But real life is not like that. So, I don't know, work with the real life situations where you might bump into things in all different ways or interact with things all over your hand. I mean, you saw that Kamakura picture, the contacts were everywhere. And so we kind of need to know that.
But for example, for the, sorry if I'm taking your time, but for a washing, you collect the demonstrations with force sensors. I guess for those kind of force sensors, since this with not humans, then is contact in us, or you think you need to explicitly use, or you will use the force reading in comparison to a kid.
I want to know the force reading there because this is looking at a problem of trying to so the way that people clean human skin is there's a range of pressures that are good, and you don't want to scrub too hard, and you don't want to be too gentle, and so there's a good range. And so I want to kind of figure out, okay, how much of the hand surface are they using in order to create that clean pressure. And I also want to understand, like, how are they using the hand in other ways to support the lens or move the body. So I'm going to use the force information we get at it here. Thank you. But again, it's all over the hand that we added. Yeah.
No, thank you very much for the talk. So this is not my area of expertise, like design, for example, of hands. I'm curious about like the weirder frontiers of hands. For example, when I do things with my hands, I pay a lot of attention, let's say, to like temperature of like the things I'm interacting with, or it's actually quite important that I can feel pain in my hands when I'm doing like really delicate work. What are the frontiers of hands that go beyond, okay, it's just touch, or it's just maybe like capability of grasping, but actually these other strange abilities.
You're right. I love these examples. So, I mean, pain is a really important one. So we think about trying to avoid damage. I mean, we could just give up and we could say, all right, the hand's going to get damaged, and welders can replace it. And that's sort of a short-term view of how to deal with that. But we, use that all the time to get ourselves out of trouble. And so I really like that example. And temperature is a really good one for sensing material differences and so on. And I think it's been very underexplored. It's not something that people have really looked at. People do have in Oliver's an example. I think he had to move, but have looked at audio signals, which is not a human-like sense, but it is also incredibly useful. So yeah. Hi.
So in the beginning of the talk, you talked about dexterity and trying to characterize dexterity with the hand. And I was wondering, do hand people worry about robustness? And there's if one little thing breaks, what's the downhill, how much is the downstream loss in performance? How does that factor?
You're talking about mechanical redundancy or something here.
Yeah, or if if something breaks, how good are we being robust? Like I broke my hand and I was screwed for 6 months.
Right. Yeah. Well, I mean that's sometimes my answer to why we need 5 fingers is not so much that we always need 5, but that gives you a degree of robustness if something happens, and it can be something breaks, or it can just be something doesn't happen the way you expected, like one finger slips off and there's another finger there to kind of catch something. So the answer to your question is people don't think about that very much, but should. And I do see like extra figures coming into play a lot of times when there are situations that look like some of the mistakes I was showing.
Right.
Thanks.
So, continuing in the same vein of out there, hand and robustness, what philosophically is the human hand the be-all end-all goal for dexterity, or is there an idea that we can do better than this?
I think that it's quite likely we can do better than this. I mean, the human hand is solving a lot of very specific packaging problems based on a particular design, and a portfolio of design choices, right? So the 2 thumbs thing I mentioned before is one that comes up a lot. If we had to, so your thumb does 2 things, 2 primary things. It does opposition, so it'll oppose the fingers in order to grasp large objects, for example, and it will oppose the side of your fingers in order to do like a key pinch, so holding your keys. And it's not very, it's pretty good at the key pinch. You can apply a lot of force that way, a lot of pinching force that way. It's not so amazing at opposition. It does okay, but the thumb pad does not exactly oppose the finger pads. So we have this kind of really weird anatomy that causes the thumb to rotate in such a way to make that work, right? So I don't know why no engineer ever makes a robot thumb that does this, and none of the robot thumbs will even work very well. So in my opinion, so I think that an obvious answer is just put another one in there and figure out how to package it in. So that's just one quick
So
example.
where do we get inspiration for that kind of stuff?
Where do we get inspiration?
For going beyond human.
I guess one way to think about it is what do you want to accomplish? If you know what you want to accomplish, and the literature is full of, okay, I know how to think about secure grasps, and there's a lot less stuff on I know how to control and manipulation now that I want to do something else. I want to move my gout. I want to change the center of mass so it's my thing is more balanced in my hand. Like I can measure that it's not balanced, but if you pick up a knife, you know it's not balanced in your hand, and you have these little strategies that you use to rebalance it, right? So I think there's a lot less understanding on what those are. Sunny is trying to look at that. He's been kind of single framing his way through a lot of videos and saying there are strategies that people use that are not uncountable. Like there are maybe 20 or 30 things that we typically do that we sequence our interactions in such a way that we manipulate objects in small ways in our hand. And I think that's very interesting. Maybe there's a taxonomy of those that we can't found.
Before I say my last question, I want to make sure that the students, are there any last student questions? Well, oh, great. That's amazing.
So people these days are interested in a couple of foundation models.
Yes.
So people learn visual motor policy from like large scale cross embodiment data set. And basically I think somebody may disagree about they are just predicting like next calls for like end effector or the robot itself. But do you think it is possible for dexterous manipulation to use like cross embodiment data set or learn so-called foundation visual motor policy using the data set from like different embodiment of the dexterous hands? And if so, what is the right representation to train that visual policy?
So you may find yourself already a little bit dissatisfied with ChatGPT. If you ask it questions and it's giving you answers that just kind of sound very nice, that they're not really answering your question, or like it made up a bunch of stuff, like it said, like maybe it made up some papers or some kind of stuff, just things that sound very good that they aren't true. So this is what I worry about. So I worry that what's going to happen is you can make up a bunch of little maneuvers that look like things you've seen people do before, but if you don't know where you're headed or what we're doing, and you don't have a good understanding of like those kind of fundamental things, you're just going to wander around and create next new poses or next new interactions that that look nice or feel nice, and maybe even they work, but they might not get the hammer to hit the nail on the head. They might not cause the robot to eventually be more energy efficient or good at what it does. That's what I worry about.
So what do you think is the right representation to learn visual motor dexterous policy?
I'm very old school, so I'm going to tell you that you can use these same techniques, but fit the old school stuff into it. Figure out how to make that work. Figure out how to understand things like, okay, where's my center of mass? Where are my centers of pressure? What am I trying to do? What am I trying to optimize? Am I trying to get a strong grip? Am I trying to shift this thing around him? Am I trying to accomplish some like apply pressure to some point in the rigid, and try to figure out how to fit that in. Yeah. That's the answer to the rest.
All right, I'm gonna ask my one last weird question before we might close. What implications from the progress we've seen in robot hands do we have for robot feet?
Yeah, that's a really fun question, because you may or may not know that the feet are very similar to the hands in their basic structure. And you probably heard the inspiring stories of people who learn how to use their feet to do all kinds of creative tasks, right? Yet the way that in robotics we've modeled feet for a long time is by, you might as well be big wooden shoes that are flat on the bottom, right? And there've been a lot of things are getting a little better now, I think, but there've been a lot of stomping humanoid robots that we've had to put up with over the years. So I think there's a lot that can be done with feet. And I would say that the folks who do the artificial feet, like the prosthetics, have done better at thinking about this and gotten more kind of creative about providing better feet. But the way that we simulate them, the way we're thinking about them in robotics, can probably be improved in terms of thinking about the compliance and so on. It's a really hard problem both for hands and feet and especially for feet, because when you try to simulate these tiny bodies like the toes, anybody who's tried that knows that your simulation is probably going to blow up really quickly, and so it's nicer to just ignore them and not think about them. But if you have systems that are already compliant and forgiving, so a lot of those problems go away. And this is where this may be a push toward please make better simulators, y'all. But yeah, I think in the real world, a lot of those problems go away because of built-in compliance.
All right, let's thank your speaker one more time.